Hey guys, I'm going to go ahead and create a video for you guys, giving some explanation of Okazaki Fragments, because it's been a real challenge for a lot of students, and I felt like it'd be a good idea to give you guys a video on this so you could revise on your own time, and it will give me a time to practice my skills with my new tablet. So, the Okazaki Fragment, guys. The Okazaki Fragment exists largely because of a problem that occurs in DNA replication. So let's go ahead and draw two strands of DNA. This one here can be the leading strand, so I'll just put L-E-A-D. And this one here down below, this one here can be the lagging strand. And I'll just call this L-A-G for lagging strand. Now, the lagging strand and leading strand are unique in some ways. So, like, essentially what happens is this. So, the leading strand and the lagging strand will come from an unwound DNA molecule. So, if I have over here, we'll just go ahead and draw the DNA, and now I have my parent strand of DNA. This is the DNA before it's copied, and you'll get a little parent strand here. And we have a helicase enzyme. Let's go ahead and change the color to a different color. And the color for this will be helicase. So I'll just put an arrow here. And we'll just call this helicase. And what helicase does is it unwinds the two DNA molecules into a leading and into a lagging strand. Now, the real trick here comes down to is the difference between these two strands. Now, the leading strand is the strand essentially where DNA polymerase can come onto here and it can just add another strand of DNA as it goes down. And the direction of replication will be in this direction. And let's add some bases here between the DNA. So this will be my brand new DNA molecule on the leading strand, and because the DNA polymerase is able to move in this direction, or oftentimes, as we like to say, it goes from 5' to 3', and that gives you how that works there. So it goes through, and it can replicate the DNA in the 5' to 3' direction. Now, a quick little heads up. Up here, the DNA is going in the opposite direction, so that would be 3, and this over here would be 5. So DNA runs in an opposite direction. Now, you don't really have to know why that is, but I can maybe spend some time at the end of the video going over some details about that, but I don't hit you too much with that. Now, on this side here, though, things get a little more interesting. Because DNA replication can only go from 5' to 3', what happens is this. So over here, we have this strand, this would be the 3, and then the new strand would be 5 up here. And that would leave over here, this would be 3 for the new strand once I make it, and this would be 5 for the older strand here. Now, here things get really difficult because DNA replication is only able to move in one direction. It's only able to go this way because of the 5' to 3' problem. So in the leading strand, it's not an issue because as helicase unwinds new DNA, the DNA polymerase just keeps on moving down the chart and keeps on making brand new DNA as DNA is added. The problem with the lagging strand, though, is as new DNA is unwound, well, the DNA polymerase can only go in this direction. It can only go towards the 5' to 3'. So you're basically making brand new DNA over here. You're unwinding new DNA that has to be turned into DNA. And it can't wait. The problem is if the DNA polymerase just waits until this whole strand here is done, well, what ends up happening is that the DNA will end up basically binding to itself in this weird little loop structure like this. It'll bind into a weird loop, and that will destroy the DNA. You don't want that, because once it's like this, well, you're basically done. Halas, finished. You're not going to be able to make a brand new DNA strand if the DNA sticks to itself like this. So you can't have a big strand here just sitting around. So the body deals with this problem by creating what are called Okazaki fragments. So what ends up happening is that a few things happen. And I'll go ahead and draw them in there. I'll draw them in red. So the first thing that happens is, actually, let's stick with the DNA. Let the DNA be black. So I'll draw in some bases here. These are the base pairs. Sorry, not base pairs. These are actually just bases. These would be like the A's, the T's, the G's, and the C's that we talked about in Chapter 12, Lesson 1. I'll draw a whole bunch on here like this. They would be on the strand here below. These are from bases that came from the original strand up here. So these things here were part of the original DNA molecule. Now, DNA polymerase is very unfortunate because it's not able to bind to empty bases. DNA polymerase cannot come onto this part right here. It's not able to attach to the part at the very beginning. It has to come in someplace else. So what ends up happening then is that the DNA polymerase needs to put something here, needs to put something in this location right here, right below this squiggly line. I'm drawing this because I'm not quite sure if you guys can see my cursor or not. That's something I'm going to learn after this video. And it has to put something here to get the DNA polymerase started. So what happens is that an enzyme, it's actually called RNA primase, but you don't have to know that. RNA primase comes in and adds some RNA here to the DNA. Because RNA primase can actually do that. It has the ability to add RNA to empty spaces like this. Once it's an RNA primer, what happens is that the DNA polymerase can now add to it. Now let's assume here for a second that we also had an RNA primer was labeled here and here. So what's going to happen is that the DNA polymerase is going to come on down. So let's make the DNA polymerase, we'll make it blue. DNA polymerase will attach to the primer right here. So this will be DNA. I'll put here P for polymerase. And it's going to attach to the RNA primer, and it's going to add bases. So it's going to come on here and add bases, going down the list, creating a brand new molecule of DNA. However, a problem occurs. When the DNA primer gets to this, when the DNA polymerase gets to this spot right here, it cannot copy over this RNA. The RNA can't do that. So the DNA polymerase goes down this chart, reaches here, and then bounces off. It's not able to overwrite this RNA. So what ends up happening is you get DNA in combination with the RNA primer in this big chunk, because it's between here and here you have a big gap, and we call that gap, we call this gap from here to here the Okazaki fragment. Now you might be curious why we call it this. Basically, a scientist from Japan named Okazaki was the one who found it. And since he found it, he got named after himself. Now the same thing would happen over here, is the DNA bases would get added by a DNA polymerase, and you get essentially 2 Okazaki fragments on this DNA. Now the problem here is that, well, you want to have DNA. You don't want to have RNA and DNA. You want to have one big DNA molecule, just like up here. You see how it's nice and simple and it's just one straight shot of DNA? You want the same thing down here. So there's a big problem. We have an RNA molecule here. We have RNA here. We have a gap right here between the 2 Okazaki fragments. Well, that's not good. You don't want that. That means you don't have a complete DNA molecule. So here's how the body deals with it. So the first thing that happens is that the DNA molecule will come in, and I need to change the size of my eraser because it's too small right now. What happens is that an enzyme will come in here and it will remove the RNA primer here, and it will remove the RNA primer here. And it removes that RNA primer. I'll go ahead and erase this while I'm at it. And when it removes the RNA primer, what ends up happening is that it leaves these blank spots. Where the RNA primer used to be, now we have these blank DNA molecules. Now you might be asking, okay, but now we had to fill these in. Well, what happens next is this, is that DNA polymerase comes back, so let's go ahead and draw my DNA polymerase, comes back, attaches itself right here, and the DNA polymerase just goes down the list. So it attaches here to the DNA here and continues on this way. So what ends up happening is it finishes up the DNA molecule. And the same thing would happen over here, is that by this point in time there would be another strand of DNA over here with another RNA primer would have been laid down by this point in time. And the DNA polymerase will then attach right here and then move this way. It'll then fill in the gap, and that will leave you with 2 more complete strands of DNA. Now it's looking more like up here. The RNA is gone, but there's still a problem. There's a gap right here. There's a gap between these 2 fragments still. So the fragment's not fixed yet. It still needs to get fixed. And that's what happens next. I'll make this in green. An enzyme comes on in and attaches this part, and this enzyme is called DNA ligase. And DNA ligase fixes this gap between the 2 DNA molecules, and these would be hydrogen bonds. And it fixes the gap between these 2 molecules, and basically you're done. Essentially what happens is that it's fixed the gap. Now the DNA ligase goes away. I'll do my best to erase this without erasing the rest of the DNA molecule. The DNA ligase goes away, and you are left with a complete strand of DNA that looks very similar to the one up here. And that's, guys, that's all that Okazaki fragments are. They're a problem that DNA replication has to deal with, and it deals with it in the method I just showed you. Now, guys, I hope that makes sense. I hope this is some good help for you guys. I'm going to go ahead and toss this video on YouTube, and I'm hoping you guys like the new tablet because I like it quite a bit. It works really well for me. And that's it. Thank you very much, and I hope this made Okazaki Fragments a little more clear for you guys.